Okay.
That's all.
Great. Okay. Thanks, Julian, for the invitation. It's nice to speak. And I think sort of the last time I talked about, I guess, this topic with Julian present would be in Taiwan a few years ago. And so there's been some developments since then. So what I want to do is sort of talk about interrelated topics of the Cone Theorem, which arises in birational geometry, case stability. And I'm interested or motivated in these topics partly because of the connection to Diophantine arithmetic geometry. So today I intend to briefly sort of explain some of those directions, but I want to sort of also try to motivate sort of a different direction for slope stability from a more birational viewpoint that's still very motivated from the classical story. So for me, the guiding questions are as follows. So there's a well established principle that ideas in geometry govern arithmetic. And so if we want to start with, rational points and projective varieties, we're interested in questions about their existence, distribution, complexity, where they accumulate. And again, it's sort of well understood that geometry governs arithmetic. And when we want to say, well, what kinds of geometry do we know governs arithmetic? And this leads to questions for stability or more refined concepts of stability, like case stability for projective varieties. And then also ideas and tools from the minimal model program in birational geometry. And so there's also, well-established connections between stability and the kinds of singularities that arise in the minimal model program, or also, when we talk about variation of geometric invariant theory quotients, certain kinds of birational morphisms that arise. So these connections here are sort of well established, but also there's a good influence to arithmetic problems. So that's kind of sort of three questions I think that help to sort of motivate the title for my talk. And I want to sort of today at least focus more on the question 2 and 3, but still give some hints to how they're related to this question 1. So the outline for today, I want to really actually go back to Mumford's geometric invariant theory, sort of the starting point of geometric invariant theory quotients as a motivation for case stability. So there's lots of different points of departure for case stability. But for today, I want to try to motivate it from Mumford's theory and essentially from the numerical criterion for GIT stability. And then I want to recall some approaches to the Donaldson-Fataki invariant, how they arise, how we can try to go about computing them. And then a very celebrated, more recent result is what's called the valuative criteria for case stability of Q-faunal varieties. And so I want to mention a few arithmetic consequences of that valuative criterion very briefly to indicate some connections to arithmetic. And then finally, sort of the main focus is the Ross-Thomas concept of slope stability along subschemes. And so this is a little bit maybe older development that sort of came before the valuative criterion of case stability for faunal varieties. And it applies to in a more general context of an arbitrary polarized varieties. And it's interesting in part because it's a more calculable or tractable kind of stability. And what I want to motivate near the end of the talk is the idea about trying to define and think about their slope stability invariance, starting from the extremal ray theory that arises in the minimal model program. And so as a slight sort of generalization of this idea about slope stability along a subvariety would be a concept of slope stability with respect to extremal rays. And so that's what I hope to get to by the end of the talk. Okay, so if we just again recall very introductory ideas to Mumford's geometric invariant theory. So remember, it's a tool for forming quotients within the category of complex quasi-projective algebraic varieties. And so it's important to remember that we talk about doing the GIT construction, for example, on a quasi-projective variety. So that's, for example, how toric varieties can be interpreted as GIT quotients. But then also when we talk about doing the GIT construction to a given polarized projective algebraic variety, we can obtain more refined measures of stability like the numerical criterion, which I'll recall briefly in a minute. And so remember, the context of geometric invariant theory is that of a reductive linear algebraic group acting on a complex polarized quasi-projective algebraic variety. And the important thing is the concept of G-linearization for the polarization. So what this means is that the group acts on X and it acts on L in a manner that covers the G action of X. And the most important examples of groups to keep in mind would be the case, for example, that G is an algebraic torus, or the case that G is the special linear group. And so when we talk about stability, the one parameter subgroups of this group G play an important role. And the first step in Mumford's GIT is to determine stability of points of X with respect to one parameter subgroups. And again, sort of the key point is that this in general depends on the G linearized ample line bundle, and the topic of that dependence, of course, is a very rich topic of independent interest. So the Hilbert-Mumford numerical criterion. So the reason I'm wanting to sort of place some emphasis on this is because I want to sort of think about this numerical criterion as motivating the question of K-stability with respect to a given GM action. And so I'll say more about that in a few slides, but for now, the context is that of a reductive group acting linearly on a polarized projective variety. And we want to fix a one parameter subgroup. And so the idea is that so the point, and it's with respect to the one parameter subgroup and the polarizing line bundle. And essentially it's determined by the fiberwise action of the one parameter subgroup. And up to a choice of sign, it can be defined in the following way. And up to this choice of sign, the Hilbert-Mumford criterion reads in the following way, that the stability of this point with respect to the linear G action on this polarized variety. So a stable means that this mu invariant is positive for all one parameter subgroups, and semi-stable means that it's non-negative for all one parameter subgroups. And so, I mean, natural question now is, can we say something more refined about, for example, if a point is not stable? Can we think about how this mu invariant depends on the function as a function of destabilizing one parameter subgroups? And so that's some of these important guiding questions for geometric invariant theory stability. So as I mentioned, a more refined study of stability is to consider stability with respect to a single one parameter subgroup. And classically, this is related to what's called the null cone, the study of the null cone, i.e. the locus of points in X that are not semi-stable. And so then, when we perform the GIT quotient, the first step is to sort of throw away these unstable points. And then we look at this quotient of the semi-stable points by G, and we get an algebraic variety. And this subscript L here is intended to indicate the dependence both on L and also on the G linearization. And so again, trying to understand the null cone here would mean, can we obtain more refined information of the destabilizing one parameter subgroups for a given not semi-stable point, for example. And then the variation of GIT quotients, this topic deals with, again, depending on studying in more detail the dependence on the quotient of the polarization and the given choice of G linearization. And that topic in and of itself already leads to very interesting birational geometric questions and morphisms. And finally, another viewpoint to the GIT construction is by the theory of moment maps and the symplectic theory of geometric invariant theory quotients. So that was developed by Kirwan and others. And I'm not going to say too much more about that today. But again, there's all kinds of interesting questions here that I think help to motivate the concept of K-stability. Okay, so now I'm going to say a few more things about K-stability. In some sense, starting from a more algebraic viewpoint, again, there's many points of departure. But what I want to sort of think about is, again, so let's think about a one parameter subgroup, or basically a GM action, a linear GM action on a polarized projective variety. And so a main goal of K-stability is to determine the sign of what's called the Donaldson-Fataki invariance of ample test configurations. And so you can think about this Donaldson-Fataki invariant as for the GM action. And one way of thinking about what are these ample test configurations is that for a given, say, normal polarized projective variety, there's a bijective correspondence for sufficiently divisible positive integers between, on the one hand, the collection of ample test configurations for the polarized variety, and on the other hand, the collection of what's called finitely generated Z filtrations of the section ring. And so kind of what's going on here is the idea is that the GM action determines a bigraded algebra, basically by looking at the weight decompositions on the section ring. And so when this bigraded algebra is finitely generated, you can take this relative proj, and that relative proj produces the ample test configuration. So that gives a works. And this sort of issue, what homogeneous degree the section ring is actually generated in. And so when it's generated in degree 1, for example, you can be a little bit more precise about how this correspondence works. But so this is a perfectly good way of thinking about, a very algebraic way about thinking about these ample test configurations, that they're essentially what are called finitely generated Z filtrations of the section ring. And so how to compute and describe the Donaldson-Fataki invariant. So again, one way is to look at the weight decomposition of the powers of the polarizing line bundle. And so then define the weights basically by looking at the eigenspaces in the dimension. And so then there's what's called the Duesenberg-Heckman measure, which is a limit of the measures sort of that are looking at how the actual eigen decomposition works. And so when you look at the Donaldson-Fataki invariant, it appears in the asymptotic expansion of the normalized weight. So here we look at the asymptotic expansion of the weight normalized by essentially the Hilbert polynomial. And we look at the higher order terms. And so this Donaldson-Fataki invariant appears as sort of some second order information. And the expectation of the Duesenberg-Heckman measure is sort of the leading order term, and then we get smaller order term contributions. And so there's some ambiguity in terms of normalization or sign or things like that. But the most important thing that we're interested in terms of the Donaldson-Fataki invariant is it positive or negative or non-negative, and that's going to govern K-stability with respect to a given GM action. Okay, so here's the definitions again. So a polarized variety is K semi-stable if the Donaldson-Fataki invariant is non-negative for all ample test configurations. And then when we talk about K-stable, again, there's some conventions we want to sort of throw out, some pathological examples. So one formulation of K-stable is that it's semi-stable, and then when the Donaldson-Fataki invariant is actually 0, this is when the normalization of the test configuration is actually a product test configuration. And so, as I mentioned, recent result is what's called the validative criterion by Fujita, building on work of Qi Li and Chen Zhu and others. And so I'll mention a little bit about what goes into that story. But if we look at arbitrary polarized variety, it remains largely an open problem to obtain an analogous validative criterion for K-stability, to my knowledge. But what is sort of analogous, at least, is the Ross-Thomas concept of slope stability along a subvariety, in the sense that it's a very sort of tractable, in some cases, way of determining instability. But still, to try to get something that's as sort of attractive as a validative criteria for Q-formal varieties, I think that's still, there's still some progress that can be made. And so that trying to sort of pick out extremal rays or my irrational viewpoint is kind of what I want to try to motivate throughout today. Okay. So before I do that, I want to say a few more consequences of the valuative criterion, just to give some hints at some of the maybe arithmetic interactions with K-stability. So here, very briefly, there's what's called Voita's main conjecture. So the idea is to start with a non-singular projective variety, for example, defined over a number field. And we want to fix a finite set of places of the number field, and we want to consider what's called a strict normal crossing divisor on X. And so what's of interest is somehow the nature of what's called the proximity function. And so the proximity function gives a measure of minus the log of the v-adic distance. So the v-adic distance, this would be for a place in the set S. So the minus log of the v-adic distance to D. So you're sort of wanting to get a measure about arithmetic closeness of rational points accumulating along D. And so the Voita height inequality gives a prediction about how that should be constrained in terms of the arithmetic complexity of points. And so that's what's called the Voita height inequality. So the conjecture says that for L, a big line bundle on X, for epsilon bigger than 0, then there's a proper Zariski closed subset, so that Voita's height inequality holds for points outside of Z. And so one important starting point to understanding Voita's main conjecture is what's called Schmidt subspace theorem. And so this is basically what these height inequalities boil down to for the case that X is projective space, that D is the sum of hyperplanes in general position, and L is the tautological line bundle. So how is all of this related to the valuative criteria for K-stability? So it turns out that for a Q-faunal variety, the valuative criteria of K-stability boils down in large part to the expected order of vanishing of the anti-canonical class along valuations. And there's still a contribution of the discrepancies, so the singularities of the Q-faunal variety. But for the special case, at least for a Q-faunal manifold, it's helpful to just even recall the case of projective space, so that if X is actually projective space and E is a hyperplane, then this expected order of vanishing quantity is actually equal to 1. So again, this is an integral of the volume of the anti-canonical class minus T times E. So, and then you're dividing by the volume of the anti-canonical class. So this is really an expected order of vanishing of the anti-canonical class along E, a divisor over X. And so again, this kind of quantity together with the singularities of a given Q-faunal manifold really amount to understanding the valuative criterion of K-stability. And so as a special case of those considerations, it turns out that you can obtain instances of these Voita height inequalities. So here's a special case of a more general statement that says for X, a Faunal manifold defined over a number field, when you fix a finite set of places, suppose that E is a prime divisor over X and having field of definition some finite extension of the base number field. And suppose that this asymptotic order of vanishing of the anti-canonical class along E is at least 1, then the conclusions of Voita's height inequalities follow for divisors of the following form. So the point is that you want to take divisors that are linearly equivalent to this destabilizing divisor, and then you also require that they intersect properly, and then you're allowed to take the sum, and then you obtain the Voita height inequalities for an arbitrary big line bundle. And so the main point that all of this is true is that after a reduction step, it suffices to establish this following height inequality. And the reason that you're able to establish this height inequality is because of this expected order of vanishing with respect to the anti-canonical class. And so this is really a consequence of the main arithmetic general theorem of Roux and Voita. And I've also studied their work in detail. And so you can think about this arithmetic general theorem as a more general form of the Schmidt subspace theorem. And this is a very another very sort of recent and celebrated result that, together with the validative criterion of K-stability, is enough to deduce certain instances of the main conjecture. So that's also something that's quite interesting. So much more can be said about this story, but that's not what I want to focus on today. Instead, I want to sort of ask this question again about what can we say about destabilizing test configurations, because that's sort of one question that this investigation raises. Okay, so with that sort of viewpoint in mind, I want to now talk in more detail about the Ross-Thomas concept of slope stability. And again, so the setting here is that of a non-singular polarized projective variety. And so an interesting question is, how do we detect K instability along subschemes? And so again, this is the approach that was developed by Ross and Thomas. And so a starting point, I'll just sort of read some of their theorems, but then I want to describe in some further detail the actual nature of the Donaldson-Fataki invariance. So their theorem is that if starting with a non-singular polarized projective variety, if it's not slope stable with respect to at least one non-singular subscheme, then it's not K-stable. And as a corollary, it follows that if a non-singular polarized projective variety is K-stable, then it is slope stable with respect to all of its non-singular subschemes. And so to get a sense, again, it's sort of helpful to recall how one actually can compute these Donaldson-Fataki invariants that arise when considering the question of slope stability along subschemes. And as I describe this, it's worthwhile sort of mentioning, again, this validative criterion for K-stability. There's certainly related ideas in the Q-faunal variety setting, certainly related ideas to the slope stability, but still it's not quite, some more important ideas are involved. And so I'll try to indicate some of those issues in what follows. So first, again, the slope stability along non-singular subvarieties. So the starting point here is just fix a non-singular n-dimensional polarized projective variety together with a codimension R subvariety, and look at the blowing up of X along Z with exceptional divisor E. And so, of course, the canonical bundle of the blowup is related to the pullback of the canonical bundle downstairs with a contribution of the exceptional divisor, R minus 1, where R is the codimension. And then one looks at what's called the Neff threshold, or the Shashadri constant of the polarized variety along Z. And so this is just gives you a measure for how positive really the pullback to L to the blowup is, how positive with respect to the exceptional divisor. So the supremum of non-negative real numbers, so that the pullback of L minus T is Neff. Okay, and so now the idea is to construct test configurations, ample test configurations for this polarized variety somehow in a way that so Z's going to have to be responsible for constructing the test configuration, and then somehow the fact that such a test configuration could be ample depends on somehow the Shashadri constant. And so that's an interesting construction. So the idea is, first I'm going to describe for you what are the most sort of important slope stability invariants for the polarized projective variety along the subscheme. And then I'll try to give some indication about how they actually arise and are related to a Donaldson-Fataki invariant of a test configuration. So the idea is to fix a number that's bigger than 0 and less than or equal to the Neff threshold. And so one can define the following quantities. So here, you should think about the slope of the polarized variety, the slope with respect to the non-singular subvariety Z, as this ratio alpha 1 divided by alpha 2, where alpha 0 is first order information of the Hilbert polynomial of L, and alpha 1 is second order information of the Hilbert polynomial. And Similarly, now you want to sort of say how much larger or smaller, depending on your viewpoint, is this slope to compared with this slope, depending on this number that's in this interval of 0 and up to the Shashadri constant. And so that's where you get this other information that is, sort of seen by the Hilbert polynomial, essentially, of the divisor pullback of L minus T times E working on the blow up. So you have this alpha 0 T, and then you have its derivative, and then you have this alpha 1 T, again, second order information coming from the Hilbert polynomial. And so then you want to combine it all in this way. And so one reason for writing all of these formulas down is that, later on in the talk, I want to describe how you can define them, basically starting from extremal rays in a way that extends this viewpoint. But then the important fact, at least for slope stability, is that these quantities are related to the Donaldson-Pataki invariant of a suitable test configuration. And so these are, computable, very computable in some cases. And that's a key point to the insight of this slope stability. So the idea is there's the deformation to the normal cone construction that really only depends on Z. And then starting from that, given this number between 0 and the Shashadri constant, there is some slight subtlety that arises when you're actually equal to the Shashadri constant. But anyways, at least when you're in this open interval, you can produce an ample test configuration. And I could have put a subscript C here because this polarization depends really on C. And so again, there's some normalization for the Donaldson-Pataki invariant. So here I've divided by 2 to help make it consistent with the Donaldson-Pataki invariant that I wrote a previous few slides ago. But up to those considerations, basically what you're interested in is this difference here. That's going to determine the sign of this Donaldson-Pataki invariant. And so this test configuration that basically determined by Z and the number C is thus not k-stable when the slope of the polarized variety along the subvariety is strictly smaller than this other slope that's depending on this number C. And so this condition about slope semi-stability along Z is this condition that you get this inequality going the other direction for all C in the interval 0 up to and including the Shashadri constant. And so that's going to be slope semi-stability. And the condition of slope semi-stable is a little bit more involved. So you want this strict inequality for all C bigger than 0 and less than the Shashadri constant. And then when you're actually at the Shashadri constant, you have to, there's a little bit more technical. There's what's called saturation question and also rationality of the Shashadri constant. But that's sort of the key idea. And so, as I said, this is a very interesting construction, partly because the numbers that appear in this Donaldson-Pataki invariant can be computable in some ways. Okay, so here's an interesting example that I came across that actually kind of sort of motivated this idea about trying to formulate slope semi-stability from the extremal ray theory. And so I think, so this is an example of Hashimoto, who I think actually was a student of Julien. And so what he did was he studied the blow up of projective space along the line. And he was interested in slope semi-stability on the blow up with respect to polarizations on the blow up with respect to the exceptional divisor E. And so I mean, a few slides ago, I talked about projective space being sort of destabilized by a hyperplane, essentially. And so this is sort of asking a different question. Can we start from projective space if we blow up a line? Can we talk about slope instability for the blow up with respect to some polarization along the exceptional divisor E? And so anyway, so in this article, he was able to establish instability. And so a question is, well, can we view such considerations from a more birational viewpoint? And so some calculations that I'll describe near the end of the talk is trying to, in the special case at n equals 3, really, just trying to compute these slopes and semi-stability invariants from a slightly different viewpoint. And what's interesting is that still, some more analysis is needed still to sort of much in the spirit of what Hashimoto has to do to sort of work out this this simple case. And so it's still it's interesting. Okay, so in order to sort of formulate how this story should work from a more birational viewpoint, I have to recall some ideas in birational geometry and pertaining to the Cone theorem. But again, before I do that, sort of in the back of your mind, the idea is to really, get at these quantities. So if we can basically define these these quantities starting from an extremal ray, then we can define a concept of slope stability in that way. Okay, so let me try to recall and describe a few things, ideas about extremal ray theory. So the idea is to study what's called the cone of curves in a projective variety. So first, just recall, so a cone in a real vector space is a subset that contains the zero vector and is closed under multiplication by positive scalars. And then we want to look at what's called extremal cones. So a subcone is called extremal if it has the property that given vectors in the larger cone with the property that their sum is in the smaller cone, then in fact those vectors lie in the smaller cone. And so the extremal rays, these are one-dimensional extremal subcones. And they play an important role in Mori's program. So okay, so again, the divisors and curves. So this is sort of quite well known to many, but just to fix notation, a key idea here is that we want to look at a pair of dual vector spaces. So we want to look at both divisors and curves on a projective variety. And the important thing is that intersection of curves and divisors, it induces a perfect pairing between the real narrow subvariety space and the vector space of one cycles. And so these are vector spaces of the dimension equal to the Picard number of X. And so the Cone theorem deals in part with the kinds of rational curves that lie in a given projective variety. And the idea is that these rational curves actually are responsible for producing contraction morphisms for extremal curves. And so I want to give a few indications about that. So here again, the cone of curves, we want to look at the following, the closure of the cone generated by irreducible curves on X. And so then part of the idea is to, start looking at hyperplanes and perpendicular spaces with respect to this intersection product of curves and divisors. So for example, for a divisor on X, we could look at the curves that intersect non-negatively with that given divisor. And similarly, for a divisor on X, we could look at the curves that intersect and have intersection number 0 along that divisor. And so we can also do variants of those constructions, looking at the intersection of the closed cone of curves with, say, the D subscript bigger than or equal to 0, and also less than or negative, and so on and so forth. And so the idea is, starting from the canonical class, for example, can we look at curves which intersect negatively with the canonical class? That's an extremely important idea. So the contraction of extremal faces. So again, we want to look at what's called a contraction of an extremal face. And so this is a certain kind of morphism from the projective variety, but it has the property that it contracts curves that are in this extremal face. And it also has what's called connected fibers, in the sense that the push down of the structure sheaf upstairs is equal to the push down of the structure sheaf downstairs. And a very important problem in birational geometry is to give necessary and sufficient conditions for existence of extremal face contraction morphisms. And so this is in some sense, the content of the minimal model program. And so it turns out, for example, there's various possibilities for contractions of extremal arrays. They could be what's called a fiber type contraction. So this is when the dimension upstairs is bigger than the dimension downstairs. There could be a divisorial contraction. And so this a blowing up morphism is an example. But the exceptional locus for a divisorial contraction, so the exceptional locus is the points upstairs where the map fails to be biregular. So this could be actually a divisor. And then another possibility is what's called a small contraction. So this is a birational map where the exceptional locus actually doesn't contain a divisor. And so the point here is that I want to sort of mention these possibilities of contraction is because if we can define a concept of slope stability with respect to extremal arrays, then hence contraction morphisms, we're getting a kind of stability that's not necessarily a divisorial contraction. So there's sort of a larger class of stability type questions that possibly arise that's not just sort of along a subvariety. And so what can we say about that? Is there any interesting structure or something along those lines? And so that's kind of the idea. So sort of first examples of extremal array contractions, just to get some sort of sense for again even what's going on in the Cone theorem. So the easiest example is in dimension 2 of the Casanova contraction theorem for a non-singular surface. If you have a -1 curve, then there is a contraction morphism, but actually that to a non-singular surface, and actually that contraction morphism is blowing up at a point of S. And so already this is this kind of question. So I mean, singularities naturally arise in the birational geometry when you start talking about contraction morphisms. And so even in dimension 2 for the contraction theorem of Casanova, for example, if you try to consider a orbifold surface, for example, it's difficult to really get the Casanova contraction theorem in general. So I made a small remark about that in a recent article. So the Cone theorem helps for sort of clarifying what kinds of contraction morphisms are natural and what kinds of singularities actually arise. Is sort of one way of thinking about it. So again, some very standard examples of extremal array contractions. So the projective bundle map is a fiber contraction. So where is the curve? The idea is the curve, the extremal curve is the class of a line contained in the fiber of the structure morphism. And this class, it spans what's called a K negative extremal array. And then another example is a smooth blow up. So this is, we really talked about this already when we were defining the slope stability along a subscheme. So again, the extremal array, if you will, is the class of a line contained in F, the fiber of the PR-1 bundle. So R is the codimension of the subvariety. And the point is that this class spans a K negative extremal array whose contraction is this actual blowing up morphism. And so sort of again, the remark here is that fiber contractions in general, they need not be projective bundle morphisms, and also divisorial contractions in general need not be smooth blowing up morphisms. And so trying to say attach some stability kinds of invariants to extremal arrays in general seems quite natural from this perspective. Okay, so in order to do that, I'll just sort of briefly recall, so there's, the Cone theorem applies to what's called a call model log terminal pair. So this is a certain kind of log pair. So the idea is that you want K plus delta to be what's called a Q-Cartier divisor. And these coefficients, they can't be too large. So you want the round down of this boundary divisor to be 0. And then you need some control of the singularity. So what's called the discrepancy of the pair has to be strictly bigger than -1. Okay. So now recalling that context, so the Cone theorem, there's several parts. One has to say, what can you say about rational curves? So there says there's countably many rational curves such that this inequality is valid, and also we can describe the cone of curves in this way. So these curves are extremal. And then also we can produce contraction morphisms by k plus delta negative extremal faces. And so this is, I mean, one way again of producing these contraction morphisms is by looking at negative extremal faces in the cone of curves. And so there's several sort of steps involved in the proof of the Cone theorem, but one is where does these contraction morphisms arise? And that's interesting, right? Because you're saying, this is the cone of curves and you have to produce a divisor somehow. And so this is steps 6 and 7 in the proof of the Cone theorem, that you actually, produce a divisor starting from, for example, a k plus delta negative extremal ray. And what happens to the divisor theory? So the Picard number drops by 1. And also, as I said before, that you have some control of the singularity. So these are sort of two important sort of points about, why these contraction morphisms are special. They have certain properties and how they're constructed. Okay, so now, given sort of this sort of background and setup, in the few minutes that I have left here for the talk, I can finally describe a context for defining the slope stability invariant. So so I hope to sort of motivate it and provide some context. And so what I want to do is sort of start with an n-dimensional KLT projective pair. And I want to suppose I have an extremal ray and I need to produce a divisor. So this divisor is what's called a Cartier divisor, which is a supporting function for this k plus delta negative extremal ray. So for example, it's the exceptional divisor of the blowing up morphism. And so I have this contraction morphism. And so now suppose that I have a big and Neff class on X prime. So L could be the pullback of an ample line bundle downstairs if this were a blowing up morphism. And so then now we define what's called the Neff threshold, or the Shashadri constant of X prime of L prime with respect to this divisor E prime. So this is exactly extending what we would say for the Shashadri constant along a subvariety. So all of these quantities make perfect sense. And so then now again we can just define these quantities. So the alpha 1, the alpha 0, the alpha 0t, all of those things, and then we can define these ray slope stability invariants for numbers bigger than 0 and less than this Neff threshold. And so we can just define this concept of slope semi-stability depending on their choice of number and depending on this divisor E prime for the log pair to be this condition about this inequality. So that's a perfectly valid natural concept. And what can we say about it? What can we study about it? And so now the idea is to maybe can we compute it? So so in a very few minutes, let's turn our attention to the very simple case, going back to this example of Hashimoto. So here, just in the case that n equals 3, what kind of quantities arise when we try to visit those calculations? And so here we have fairly detailed knowledge. So for example, we can view this as a projective bundle over P1. So this is the P2 bundle of hyperplanes in the fiber of the projectivization of E. And so then now the blowing up along the line is the map that's determined by the tautological bundle. And so here we can actually compute the Chow ring very explicitly, and we can represent the various divisor classes in the usual way. And so now we can just compute. And so when you do those calculations, this is what you end up getting. So here's would be an arbitrary, so L would be an arbitrary ample line bundle, and you do the calculation L minus T, you can rewrite, and then now you can compute these quantities in a very explicit way. And then finally, you can compute the slope. And then again, this is this mu c constant that appears. And so that's what these are. And so already, again, there's still some work to deduce the result for n equals 3 about the destabilizing. But it still suggests that this can be computable in some ways, and that there's some structure there that's interesting and that could be developed possibly in some further detail. But on the other hand, yeah, I don't know, for example, what some of the theorems could be. You could, for example, deduce slope stability along a subscheme if you know it's slope stable along all extremal rays or something like that. But beyond that, I'm not sure what exactly can be done. But I thought it was interesting to try to at least think about these calculations from the extremal ray theory. So anyways, so I should probably stop there.
Thank you so much for the talk. Are there some questions or remarks? Actually, so I wanted to know. So there's this definition of you do a definition of slope semi-stability for a KLT pair for L prime, which is a big NF. That's correct.
Yep.
Okay. So how does it relate? I mean, okay, so that's different from. So is there a notion of K stability with respect to big NF line bundle? I don't think so. No, it's only with respect to polarization, right?
Yeah. So this is a good question. So in some sense, this viewpoint is wrong to sort of approach from the classical definition of K stability, if that makes sense. What it is natural is if you take slope stability along a subvariety as your point of departure, then this kind of viewpoint becomes more natural. And the reason is partly because this very again sort of motivational example about the slope stability of the blow up of projective space along the exceptional divisor. And so, right, because slope stability still is sort of more thinking about slope stability of the variety downstairs with respect to a subvariety, because you can construct a test configuration upstairs. But here, right, this example is already saying, well, actually, we're going to look at slope stability of the blow up with respect to this exceptional divisor with respect to a polarization on the blow up, and we're going to ask for slope stability. And so what that is doing is saying, well, we're going to look at slope stability of X with a prime with respect to a polarization L prime with respect to the exceptional divisor thought of as a supporting function of an extremal ray.
And in the case the example you took at the end,
yes,
do you get slope semi-stability?
So these numbers are these in the end. This calculation is going to boil down to the exact same calculation that he for n equals 3. But still to sort of actually deduce the conclusion, it's still slightly involved as he does. So he has to. So it's not entirely obvious to deduce even in that case starting from here, unfortunately. But that's how it. But that's how it sort of works out. But this is what I mean when you do the calculations, right? This is exactly what these calculations are. Does that make sense?
No, my point was just to know. I mean, you have this definition of slope semi-stable.
Yep.
So is P of E with E the direct sum of the two line bundles you are considering stable in that sense?
Along the exceptional divisor. So
along the exception, yeah.
For certain values of C, the answer will be no, right? Because this is exactly the blow up of P3 along this line.
Okay.
Right. So the reason, so this example will recover, right? It will boil down to the exact same calculations that arise for.
I see.
For this example. So it's just approached from a slightly different viewpoint, even for the special case n equals 3. But setting up the calculations from that direction suggests a way of doing that, in general for extremal arrays. And what more can be said? I mean, at the moment, I don't know.
I see. Interesting. Okay. Are there other comments or remarks from the audience?
I'm a little curious about the connection between arithmetic geometry, this beta invariant. When you say beta greater or equals to 1, so for projective space and the usual polarization, you have that condition, and beta is equals to 1. What's the connection with the slow stability?
Okay, so that's a good question. So in general, that's difficult to say. And so I should mention that the notation for the valuative criteria for K-stability of Q-Final varieties, this beta quantity is not the usual beta. I think it's usually somehow S or something like this. So you can look in Fujita's paper, and so the inequalities that appear, again, there's also a contribution of what's called the discrepancy of the Q-Final variety. And the valuative criterion is talking about, what are called, it's reduced in the end to what are called dreamy prime divisors over the given Q-Final variety. And so you have to construct test configurations. But the point is that those test configurations don't necessarily arise from the deformation to the normal cone construction. So there's more is needed. So you're getting filtrations of the section ring that are similar, but sort of strictly speaking different. And so that's kind of, the short answer is it's more subtle. And so that's why, when I was trying to explain in some detail about what is the actual shape of the Donaldson-Fataki invariant that arises when you talk about deformation to the normal cone and slope stability, there is an actual test configuration which actually has Donaldson-Fataki variant in this direction. And so maybe your question is, does, even in the Q-Final variety case, does this expected order of vanishing quantity arise in a direct way by the deformation to the normal cone slope stability condition? And the short answer is not direct, like it's a little bit more subtle than that. Does that answer your question?
Yeah, I think my question is more multifaceted.
Mm-hmm.
So you talk about divisorial, I mean, not divisorial contractions, but the slope stability along subvarieties.
Yes.
So is that related to divisorial stability or semi-stability?
The short answer, yeah, I mean,
upstairs maybe?
Yes,
upstairs?
well, okay, so the short answer again is yes, but again, still it's a little bit, the story is a little bit more subtle than that. So one viewpoint is the paper of Boxum, Hisamoto, and Janssen, where they ask the question about, there's what's called the Riesz valuation of a subvariety, or the Riesz valuations. The subvariety could have several different components. And can you construct a test configuration basically which sort of sees that Riesz valuation, in the sense that the bigraded algebra that you obtain is a Riesz sort of algebra. And so you can prove theorems like that. And the filtrations that arise are similar, or slightly more general even, than the deformation to the normal cone construction. And this is also Fujita's construction of what he calls basic test configurations from a dreamy prime divisor. And so those are constructions, and the Fataki invariants there, especially in the Q-Final variety case, boil down to much more this beta invariant as I defined there. So that's I mean, yeah, so that's partial answers to your question. The short answer is in some sense yes, but in some sense it's also more slightly more subtle. But you can kind of see that still in this the asymptotic expansion of this Duesenberg-Heckman measure, how the Donaldson-Fataki invariant is somehow second order information, whereas this Donaldson-Fataki invariant appears as sort of, perhaps you could say it is. I mean, it's more directly related to this expected order of vanishing beta type invariant.
So it's I guess the Donaldson-Fataki invariant has some similarities to this beta, but not directly related, I guess. I mean, there's
in general, it is directly related in some cases. For example, the dreamy prime divisors in a Q-funnel case.
Okay.
Okay, but in general, I mean, the important formula to keep in mind is this entire sort of the totality of this asymptotic expansion, and part of the deformation to the normal cone or the slope stability procedure is that things can become more explicit, and that's why it's a more tractable kind of stability.
Dreamy prime, the dreamy.
Well, especially for the dreamy prime device, that's even more refined in the Q-funnel setting.
Well, that's a special case, but it's an important special case, and probably
very important.
The other cases are maybe may fall similarly. I don't know.
Well, for a general polarized variety, I'm not sure. But for the valuative criterion for case stability of Q-funnel varieties, in the end, it boils down to the dreamy.
Yeah, but you're looking at it. I mean, you're talking about collections of test configurations. So probably there's some local thing that happens that you can extract out of this. Anyway, I'm just guessing.
No, yeah, exactly. I mean, for the arbitrary polarized case, I mean, is largely open for like a true valuative criterion, to the best of my understanding.
Thanks.
Yep. Thanks.